Hello, I'm going to talk to you about co-design for Edge Artificial Intelligence, application-specific system on chips. I'm Dr. John Wolbier. I'm a senior research scientist and advanced computing lab lead at the AI division at the Software Engineering Institute. The agenda for this talk is to describe to you what an application-specific system on chip is, accelerator design flow, how do you design accelerators that go into these SoCs, SoC integration, how do you combine the components to make the full SoC, and then prospects for this work and additional resources if you'd like to try to do some of it yourself. So first, application-specific system on chips. What is an SoC? So edge devices such as drones are powered by microelectronics. All sorts of microelectronics contribute to the operation. These include accelerometers, cameras, flight controllers, GPS modules, speed controllers, and radios, for example. The radios I have there is TX-RX for transmit receive. What is a system on chip? Well, you can think of one of those chips in those microelectronics in the top image and exploded down into the bottom image. One chip has many functions that comprise a system. The kinds of components that go into one of these systems include CPU cores, that's for central processing unit, GPU cores for graphical processing unit, memory cores, or accelerators. Examples of accelerators would include accelerators for specific functions like fast Fourier transform, that's FFT, or natural language processing, that's NLP. NVDLA is NVIDIA's open source AI accelerator. And then I have the transmit receive for radio kinds of applications. So that's what an SoC is, one chip that goes into that set of microelectronics that might appear on, for example, a drone. So what makes them application specific? So when the mix of the components on the SoC is designed from a specific application. So if your application does object detection, object classification, or radio frequency signal characterization, for example, you can design specifically your chip to match your application set. It turns out that electronics efficiency plays a major role in system performance, and designing an SoC for a particular deployment can yield major benefits. So for example, the quote at the bottom of the slide talks about how compute can improve mission time and lower energy consumption by as much as 5x. So if you can design an SoC for your specific application, your application and mission can greatly benefit. So how does one go about designing an SoC? So on the left-hand figure, we have a tile. So what you want to think of that as the chip, and I'm going to put different pieces of specialized IP or intellectual property into each one of those squares. And so how do I do these? How do I design these things? There are several methods. The most detailed is a hardware description language. A hardware description language you can think of as software, but that software designs circuits, not implements functions, for example, in a traditional, as you do in a traditional language. So that's the lowest level. The next level up is something called high-level synthesis that we're going to talk a little bit more about in next slides. High-level synthesis tools include Bamboo, one API from Intel, and the AMD Xilinx set of high-level synthesis tools. And I'll describe a little bit more about what that means in a bit. Once you have these sort of component pieces, one can use a framework such as ChipYard out of UCLA Berkeley or embedded scalable platforms out of Columbia University to integrate all these pieces up together and make the final SoC. What we have here is an example that is given to us courtesy of the IBM EPICS program, which was funded by DARPA, showing an actual instantiation of an SoC with different accelerators in the different spots. So starting from the upper left, you have a tile that is responsible for input-output. Going across to the right, natural language processing, EdgeBird accelerator. I won't go through every single one, but there's a square there. The Ariane block, that's actually 4 RISC-V CPUs The bottom right one of those being a RISC-V CPU plus an inline accelerator. We also have an NVIDIA cores, FFTs, et cetera, et cetera. Like I said, I won't go through all of them, but that's the notional system on chip, but it's also a real example. So the first step in getting to your system on chip is to actually design an accelerator. So what you want to do is you take your application, you identify hotspots in your application that you want to accelerate, because you can determine that acceleration of these particular pieces of the application would improve the energy efficiency of the whole system. Possibilities for doing that, hotspot identification include traditional profiling, but then also sort of annotated source code analysis. And there are lots of techniques around that to identify accelerators. And then there's never a substitute for expert knowledge when deciding how to take your overall application and turn it into a system on chip. So you've identified your accelerators that are the pieces of your application that you want to accelerate. What are your options? Well, we're going to come back to HDL and HLS again. HDL was, remember, the hardware description language, and this is software that is used to implement circuits. And so one could actually write the hardware description language by hand to implement their accelerator. This turns out to be very time consuming, but it is the way one can achieve the optimal performance. The next level up is high-level synthesis, and again, these are tools that take more traditional source code, C, C++ kinds of code, and lower it to a hardware description language. These tools are much faster, but you're unlikely to achieve optimal performance. So, and in particular, we're talking about AI systems, and so how is most AI code implemented these days? Well, it's in Python, it's in PyTorch or TensorFlow, these high-level languages that are used to implement neural networks, and HLS, high-level synthesis, supporting PyTorch and TensorFlow, for example, are fairly new technologies. And they're immature. And so we're going to talk a little bit about one example of this and how it can be used to get from your Python code to an accelerator that you're going to put in your system on chip. I also want to just make one mention of emerging approaches. I won't talk any more detail about this, but multi-level intermediate representation is a very popular compiler framework for model lowering. What MLIR is it's a set of dialect abstractions where one can start from a high-level source code and incrementally lower it towards either hardware object code, or in our case, we're trying to lower towards a circuit design. So this is a very popular approach. We have some activities in this, but I won't be talking about them in this talk. So we're going to go to an example. We're going to take a real simple 3-layer neural network that's implemented in PyTorch and sort of show you the steps or cut to the chase for how this is implemented as an accelerator. PyTorch Iris is the neural network that we're going to talk about. We wrote it, but it's ubiquitous. You see this implemented everywhere on GitHub. It's in a lot of ways one of the first networks that someone does when they're starting to learn about how to do machine learning. So the network itself is a linear layer followed by a rectified linear unit, or ReLU, followed by another linear layer, then a ReLU, and then finally by a softmax. So it's a 3-layer neural network, and it's about as simple as you can get. Looking at the code down below, you can see all those components. In the model definition, you say I have a ReLU, and I have 2 linear layers with the given input dimensions and output dimensions, and I have a softmax. And then in the forward function is where you actually implement, X comes in, you put it through the linear layer, then you ReLU it, then you put it into the next layer, and you ReLU it, and then you ultimately output the softmax. So that's the neural network that we're going to be talking about. So what we do is we feed this neural network to a tool in this case called HLS for ML. That's high-level synthesis for machine learning. This is an open source tool that you can find on GitHub that works with PyTorch and TensorFlow to lower your Python neural networks to circuit design, hardware description language. In our particular case, we're going to use HLS for ML and the AMD Xilinx set of HLS tools backend to do the synthesis. One of the things that you do when you're doing the synthesis is you decide about how you want to represent the information in the neural network. Traditional sort of off-the-shelf PyTorch TensorFlow will use floating point representation, whether it's floating point 32 or floating point 16 or something like that. In this case, when you're lowering to hardware description language, you typically want to go to a fixed point quantization. And in this particular case, we're going to use 16 bits to represent our data, where 6 bits are used to represent what comes left of the decimal point in this fixed point representation. And HLS can be thought of as code to circuit. I start with the code below, I run it through this set of tools, and I get a circuit. On the left is a picture from Xilinx Vivado showing what circuit came out of this process. And if we zoom in, one can actually go and you can match up sort of the individual blocks with the numbers of neurons in the neural network. And so once you've done this, you are in a place where you have a hardware description language description of your thing that you want to accelerate. In our case, it's the PyTorch Iris. So now we have that. How do we integrate that into a system on chip? All right, so what we're going to do in this case is we're going to use a tool that comes out of the University of Columbia called Embedded Scalable Platforms. It's an open source tool that we were introduced to a couple years back. On the left is sort of the graphical representation of what you see when you open up ESP to design your SoC. So what you want to think of is in the grid in the sort of middle there are the tiles in your SoC. There are fields on the left where you can change the number of rows and columns you want in your SoC, but we're just going to take the default version here that has a memory tile, it has a CPU tile, it has an empty tile, and then it has an I/O tile. So we took our accelerator, we integrated it into ESP, and now we can actually do like a pull-down menu, pick our accelerator from the list, and then plop it into that lower left corner there. And so now we have an SoC that's going to have a memory tile, a CPU tile, our Iris accelerator design, synthesized with HLS for ML, and followed by an I/O tile in the lower right. So now one has a couple choices. So from here, you can either implement it in an FPGA, a field programmable gate array, which is what we're going to show. But there's also an option at this point to say, I want to actually design a full application-specific integrated circuit. How do I do that? Well, ESP supports that flow as well. We won't do that in this talk. It's a much more involved process, but that is there. So we're going to implement this on an FPGA. So this is a picture from our lab. Two pictures from our lab of the same board. This is a FPGA VCU 118 development board that's connected to a host computer on the left that's actually not shown. You can see the board is connected to the host by several different connections. The ones coming in on the lower right, there's a JTAG and a UART connection, but then also the Ethernet connection that's connected to a router and back to the host. The actual FPGA, the field programmable gate array, which we're going to put our system on chip in is under the fan in the picture on the right. And so our system on chip is it's a fully functional Linux system. And so what we're going to show in the right-hand side is our system on chip that includes the CPU and the accelerator, like I talked about, actually booting Linux. And so at a 3 times accelerated pace over what it actually runs at. So it's booting, the accelerators appear near the bottom there. One logs in to the Linux and changes to a directory and actually runs an application that invokes the accelerator that does the neural network that we set out to do. So that's a full cycle demonstration of making a system on chip with a particular accelerator for a very simple neural network. So this is a 3-year project. We are at the end of the first year, and so we've demonstrated the full cycle of doing the SoC integration. And so what are we going to do next? Well, we're going to, we have an application that has a workload that's much more involved than just the 3-layer neural network, and so we're going to move on to that. So, for example, ResNets appear in our application. The application is actually a digital signal processing application that would fly on a drone, and so the next steps are to take the real neural networks that appear in the application and push them through this so-called design flow to get the accelerator for the neural net as it appears in the application, and then ultimately the system on chip. What's done then is the energy quantification. So you've done all this work. What did you get? Well, you can demonstrate that you've achieved energy efficiency improvements, which will improve your mission metrics of your drone in this case. And you want to do that. You want to prove to yourself that you've achieved mission metric improvement, and the way you do this is by integrating that simulated and demonstrated efficiency improvement. You integrate it into a higher level simulation of a drone to show things like improved flight time or improved average speed of your drone, for example. So those are sort of the things that are coming in the next year and third year as well. That wraps up the technical content of my talk. I've got some resources here. So on our CMU SEI GitHub, there's a couple open source repositories that you can go to, and you can, in principle, you can fully reproduce this work. The first is the PyTorch Iris. Again, this is not unique to us. This is a neural network that you can find all over GitHub, but if you want to use the specific one that we were using in this work, there's a link to that there. And then there's a couple of Docker environments. One is for HLS for ML. So the process of actually taking your neural network and getting it to the hardware description language is an involved process. But that if you go and you use that Docker environment, you should be able to have success. And then lastly, a Docker environment for using ESP. That's Embedded Scalable Platforms. That was the SoC integrator package from Columbia University. So there's a Docker environment there. To do that process is also quite involved, and you might find the tutorials at the last link useful for those steps. So with that, I'm all done. If you have any questions, I'd be happy to take them. Thanks.